So next up, we are going to formally discuss acid-base chemistry from an equilibrium standpoint. And this is probably a fairly important character string. So you could express any generic acid as HA, where that H basically represents a proton that's about to be donated. And acids in general have a very specific reaction with water. So they will react with water and achieve an equilibrium with hydronium. So in this case, the water is acting as a base. It's accepting a proton. So the water, we'll say, is liquid. The hydronium is aqueous. And then what's left is whatever that acid was minus the proton, and we just call this A minus. Again, so we've lost an H and we've reduced the charge by 1. Now, what is the equilibrium constant expression for this generic reaction? So this is practice. Hopefully after the last set of videos you know this, but it would be equal to the concentration of the products, so the hydronium concentration, the concentration of the conjugate base A minus, divided by the concentration of the acid. You will note that the water doesn't show up in there because water is a pure liquid in this case, and those don't show up in equilibrium expressions. All right, and ignore. Whoops. Let's do that. Okay. Now, this is an equilibrium expression. It's just like all the equilibrium constant expressions that we've dealt with before. This one, the powers that be have deemed important enough to give its own subscript, and this is called Ka. And that just stands for, that A just means it's the acid dissociation constant, but it is an equilibrium constant just like the ones you've seen before. All right, so let's do an example for this. So this is straight from the group activity that I would have had planned for you all today. So a solution of nitrous acid, HNO2, the HNO2 concentration is 1.33 molar. The hydronium concentration is 0.026 molar, as is the nitrite concentration. So what's the Ka for nitrous acid? Well, this is about as simple plug and chug as you can get. I would recommend when you're working problems like this, until you become very, very, very familiar with it, that you write down the actual reaction or even the equilibrium, which is what I should have put here. That you're working with. And here, so we're talking about HNO2 donating a proton to water to form hydronium and the nitrite ion. So let's do a little bit of other labeling here while you're at it. So label the acid, label the base, and label the conjugate base and the conjugate acid. So acids and bases come from the reactants. So this HNO2, again, it's called nitrous acid, so that was probably a hint. It's donating the proton, so it's acting as the acid. The water is acting as the base in this case. And if you look at it in the reverse direction, then the hydronium, so the nitrite, I should start with there, is what's left over from the original acid. So this we're going to call the conjugate base. And the hydronium is what became of the water after it accepted the proton. So that's going to be the conjugate acid. And then, so what's the numerical value of Ka? I'll just plug into the equation. So it's going to be the hydronium concentration times the nitrite divided by the HNO2 concentration. Plug in the numbers, and you should get 5.1 times 10 to the negative 4. Now, keep in mind what this means, and look at these relative numbers right here. That in this particular case, the concentration of hydronium and nitrite is quite low relative to the concentration of the HNO2. So what you can imply from this is that when you put HNO2 in an aqueous solution, some of it undergoes this proton transfer reaction with water, but in fact most of it does not. Most of it actually remains as HNO3, or I'm sorry, HNO2. And this is why we call this particular one a weak acid. Most of the molecules actually do not undergo the proton transfer with water. Some do, some don't. So let's look at a table. So this is a list of acids. And I will tell you that clearly you'll see that there's, this line right here is not an accident. And the ones above that line we refer to as strong acids, and the ones below that line we refer to as weak acids. So review the names. These are names that you should actually be familiar with, but look at the numerical values for Ka. So you will note that the one that we just did, nitrous acid, is right there. So let me ask you a question. Look at those numbers. I'm going to ask you two questions. And look at the Ka values. What seems to make them strong, and what seems to make an acid be classified as weak? Well, hopefully you've seen that there's actually a pretty large disparity in the values of these numbers, and that all of the strong acids all have Kas that are larger, and in some cases much larger than 1. So what does that mean? Well, actually, let's look at Kas. I'll draw this here. So generically, Kas are H3O plus A minus over HA. So what does that mean? For these guys, for a Ka to be 10 to the 6th or 10 to the 9th, that means that the hydronium and conjugate base concentrations, A minus, are very, very large. And the concentration of the acid must be quite small. So big denominator, big numerator, small denominator makes the result a very, very large number. So what makes an acid weak? Well, the Kas for the weak acids tend to be less than 1, and in many cases much, much less than 1. So in this case, that the concentrations of H3O plus and the conjugate base are quite small, and the concentration of the unproton transferred acid are actually quite large. So small numerator, large denominator, your result is going to be a small number. And these are 10 to the negative 3 all the way down to 10 to the 16th. So now we talked about this really, we barely touched on it in a previous chapter, saying that strong acids completely reacted with water, weak acids just only partially so. And here we can actually quantify this now, exactly how much they do that by. So this is kind of like now a numerical way to scale strong acids and weak acids. So now I will ask you to focus only on the weak acids. And so let's say that you had a 1 molar solution of each of these. Which would you expect to have the highest hydronium concentration, and which would you expect to have the lowest hydronium concentration? So think about it for a sec. Okay, so basically you're looking for, for the first question, you're looking for the largest Ka, and that is phosphoric acid, the H3PO4. Now remember that we're looking only at the weak acids, because basically the idea is for the strong acids that they all just basically completely react with water. So for all of the strong acids, if you had a 1 molar solution of the strong acid, you would pretty much have 1 molar hydronium. Now going back to our questions here, the lowest of the hydronium concentration with the weak acids, there you want to look for, and I think I want to accept water here, so let's not deal with that one. But so accepting water, which one is going to have the lowest hydronium concentration? So in that case, you would want to look for the lowest or the smallest Ka, and that, if you look carefully, is hydrosulfuric acid H2S, which is the compound responsible for the wonderful odor of rotten eggs. All right, so this is now with Kas we can quantify, what's a strong acid, what's a weak acid. All right, let's play this game a little bit more.